Hey viewers, you're welcome to Science Spectrum with Don. This is the second lecture, but the third part of the second lecture precisely in PHS 187, which is the fundamentals of physics. So this will be a continuation of the powers of 10 or orders of magnitude, and of course we'll stretch this to derived physical quantities. All right, so we'll talk about the positive power of 10, positive powers of 10. Powers of 10. All right. Okay. So I will start off with 10 raised to the power 1, 10 raised to the power 2, 10 raised to the power 3, 10 raised to the power 4. These are the orders of magnitude. Okay, let me use 6, 10 raised to the power 9, 10 raised to the power 12, 10 raised to the power 15, 10 raised to the power 18, 10 raised to the power 21, 10 raised to the power 24. This is deca. This is hecto, 100. This is kilo, which means 1,000. This is mega, that's a million. This is 10 raised to the power 9. This is giga, or you could pronounce it as giga, like from the word jiggle, the way the Americans call it. But I'll prefer to use giga. Then this is tera, 10 raised to the power 12. This is peta, 10 raised to the power 15. This is exa, 10 raised to the power 18. This is zeta, 10 raised to the power 21. And this is iota, 10 raised to the power 24. These are the positive powers of 10. And it interests you to know that we associate these powers of 10 to SI units to quantify relative amounts of physical quantities. All right, now we stretch this now to derived physical quantities. So we stretch this to derived physical quantities. All right, derived physical quantities. All right, what's a derived physical quantity? Simply a combination which implies the products or the quotients, which is the division quotient of two or more fundamental physical quantities. That's the derived quantity. Now, in tabular form, I would write the quantities, of course, the units, and of course I'll talk about the dimensions. All right, so we start with the first one, which is area. Area tells you is a quantity that describes the space within an object. And for my simplicity, I could use the area of a rectangle, so which is defined as the length times the breadth. That's for a rectangle. All right, the length, the breadth, they mean the same thing. Breadth is the form of length. So length would be in meter, breadth is in meter. So this would give us meter times meter, which translates to squared meter. And of course, the dimension for length, whose unit is the meter, is L. And of course, this is raised to the second power. All right, then we'll go to volume. Volume, or the capacity of a substance. Volume is simply the area of that object times its perpendicular height. Area is in square meter, height, which is the form of length, is in meter. So square meter times meter translates to cubic meter. And this is the dimension for length, whose unit is meter, is L. And of course, since its volume is raised to the third power. Now, we could describe an object in terms of a quantity, which is its speed, how fast the object travels, which could be in a straight line or not necessarily in a straight line, or we could use the word velocity. Alright, now speed is defined. The speed is defined as the actual path length an object travels, or we say the distance per unit time. Just say over the elapsed time. And of course, distance is a form of length, and time is in seconds. So this is meter per second, which is meter per second. Meter is unit for length, so we measure speed in meter per second. And of course, if it had been velocity, this would be displacement, which specifies a vector now that we are taking into account directions. Alright then, per time. So speed, velocity has the same unit. Now, the dimension for speed is L, that's meter is unit for length. T, this is raised to power minus 1. Okay, that's for speed of velocity. Now, we could go to the acceleration of a body. Acceleration, the rate at which an object's velocity is changing. Now, acceleration is simply the change in velocity per unit time. So, it's this quantity, this unit, divided by time. So, this will translate to meter per second times. This I have over second, this is per second here. And of course, this will give us the law of indices, pick one of the base, since they are the same, add the powers, minus 1 plus minus 1. Plus and minus will translate into a minus, and minus 1 gives us minus 2. So this is meter per second squared. And of course, this is L, T raised to power minus 2 with a square bracket. This is the dimension for acceleration. Now we could go to force. The force. Force is simply the product of the mass of an object times its acceleration. So force is mass times acceleration. Mass is in kilogram. Acceleration, we could read it off here, is meter per second squared. So force, when expressed in terms of its base quantity, is kilogram meter per second squared. But its derived unit officially should be in Newton. So 1 kilogram meter per second squared is the same as 1 Newton. Now the dimension for force, we could read it off from its fundamental units. Alright, this is kilogram is mass, M. This is L. This is T raised to power minus 2. And of course, this is the dimension for force. And of course, we could go to pressure. Pressure is simply the force, perpendicular force, that acts per unit area of a substance. Force is, in terms of its fundamental units, that's kilogram meter per second squared, divided by area, that is, its unit is square meter. You could see, I could lose 1 m. Then this is, we are left with kilogram per meter, 1 over m now, per second squared. Now, this is when we express the unit of pressure in terms of its fundamental unit. But officially, pressure, its unit is given in Pascal. So 1 kilogram per meter per second squared is the same as 1 Pascal. And of course, its dimension, we could read it off from its fundamental quantity, that's fundamental unit, so to speak. This is mass for kilogram, L for L raised to power minus 1, and this is T raised to power minus 2. This is the dimension for pressure. Now we could talk about work or energy. Work or energy, still with this same pattern. Work or energy. Work or energy. There are two synonymous words. Now, what is simply work? Work is force, exerted force, times the object's displacement. Force, when we express force in terms of its fundamental units, we could read it off from here. This is kilogram meter per second squared times, displacement is of course a form of length that it needs to be in meter. So this will translate to kilogram squared meter per second squared. So if we express the unit of work or energy in terms of its base units, this will give kilogram squared meter per second squared. And of course, officially, the derived unit for work or energy is in joule. So 1 kilogram squared meter per second squared should give us exactly 1 joule. So this is the derived unit for work or energy. And of course, the dimension we read it off from the base units. So for kilogram, that is M. This is L raised to power 2, T raised to power minus 2, and of course, once I enclose a square bracket, we talk about its dimension. And of course, we will talk about power. Power, the rate at which work is done. Power, rate at which work is done. So it's just simply work done or energy divided by time. And of course, work is kilogram squared meter per second squared over time. Over time, that's over second. And of course, this will translate to kilogram meter raised to power 2, second raised to power minus 2. Of course, I have 1 over second downstairs, that is times second raised to power minus 1. So this will give kilogram squared meter per second squared. It's the same base, and then the times in between, I'll add up the powers plus minus 1. Now you could still write to your own very eyes that power expressed in terms of its base units will be kilogram squared meter second raised to power minus 3. Or this is joule per second. We could use joule per second. But officially, power is measured in a unit called watts. Now its dimension will be M L squared T raised to power minus 3. Now we could have density. The density is mass per unit volume. This is when we talk about volume mass density. This is in kilogram, and this is in cubic meter. So this is kilogram per cubic meter. So this is kilogram per cubic meter. It's the same as its derived unit. So this would be M L raised to power minus 3 with a square bracket. And of course, for the sake of time and YouTube's policy, I can't really make a video that would exceed 15 minutes. So in a subsequent bulletin, I'll proceed from here. Thank you for tuning in. You may want to like, share, and subscribe for more content. Thank you.